All right, it's 5:25, so let's get started. So P-Set 4 is due on tomorrow. Any questions about P-Set 4?
Do we have to articulate every algorithm, or can we?
It depends on the problem. Any?
The algorithm for number 5.
Which one was that again?
That one was the minimizing NSA.
Okay. Mm-hmm. Yeah.
We do?
What do you mean articulate the algorithm?
As in specifically call out and write up an algorithm for
minimization. You'll be making a decider that, or supposedly a decider that will take in arbitrary NFA as input, so like on input,
right.
Where it's an NFA, then list out steps that will accept and reject appropriately.
Okay. So if I split those into my independent algorithms, I say run the algorithm, and then this algorithm.
Yeah. So like if for example, if you want to run convert this NFA to a DFA, that's fine. If you want to run E sub DFA, just say run E DFA on this.
Okay. And so if I have the algorithm, I can just reference the algorithm, and then based on that, I can make the whatever decider.
Yeah.
Okay.
Mm-hmm. And you'll have to say whether or not your machine that you make is a decider, and so therefore it always halts on all inputs.
Okay.
Yeah, you have to prove that your result actually does halt, but yeah.
Got it.
Yeah.
If I try to take the algorithm with 3,
Mm-hmm.
say for making sure that
It's the power L one, right?
Yeah.
So you'll be making a recognizer for power L, which takes in an arbitrary string W, or whatever you want to call it, and says except if it is some string repeated multiple times that was in the original recognizer's language.
So that the part where it determines if there is a repeated string over and over,
Mm-hmm.
and give the algorithm for that.
Yes. Mm-hmm. Mm-hmm. Other questions about P-Set 4? Okay. Any questions about P-Set 5? I know I just posted it not too long ago. No questions about P-Set 5. Any other questions at all? Yeah.
Regarding the cheat sheets for the final exam.
Yep.
My argument for why we should have more sheets is you make us handwrite them. So handwriting more information would help us study more, and it would give us more tools to use on the exam.
You should be a lawyer.
Yeah. Yeah, but so that is a good argument, but the thing I'm worrying about is that people are just going to be spending, I've seen this happen many times, where people just look at their cheat sheet hoping that they'll find an answer. Trust me, you won't find it. That's directly on your cheat sheet, but it's helpful in case you forget something that maybe that non-deterministic Turing machines and deterministic ones are equivalent, for example.
I have an argument for against, and I know people are going to hate me, but I wanted to put it out there anyway. Is that
you have the floor.
it's good study practice to rewrite it again, and you're not going to need everything on both old cheat sheets. If
Yeah.
You already have your other tests.
Send me an email if you have an idea of whether you want to have more than one or just want one, then I'll give an announcement probably next class. Okay? Any other questions in general, though? Remember, the size of the paper is not bounded, other than distracting the person next to you. But other questions, though?
Are we limited to, can we tape 2 pieces together to make one set? Or are we limited to actually manufacture of one
I'd
piece?
very much prefer not.
Okay.
But because, I mean, you could fit some, yeah.
True, true.
Yeah. I'd just rather have everyone have a fair opportunity. Yeah. But I'll let you know. Other questions, though? Okay, so we were talking about P and NP last time. So what do you think P stands for? Well, yeah, polynomial, and we were talking about it in the context of time. The amount of time for a Turing machine to compute, to answer a particular question about some language, whether a string belongs to some language or not. And so P represents polynomial time. So I just copied the definition we talked about last time. So we talked about this thing called time, which is the set of all languages that are computable within some constant times the amount of time in the argument. So here is just a constant times n to the k, and for all inputs of size n, and we wanted P to be the union over all constants k. So for whatever constant you want, say n cubed, that's in P, for instance. But any constant that you want. And then we've defined an analogous one for non-deterministic machines, which is called NP. So what do you think NP is called, an acronym for? Yeah, so that's something that is not only a misnomer, but also is close to what people actually believe. So it's kind of weird. It means non-deterministic polynomial time, officially. So I'm not going to write polynomial a couple hundred more times. I'm just going to write poly now. But we believe problems that seem to be in NP but not in P to not be polynomially solvable, and we'll see that later today. But as we noted last time, we saw that P is a subset of NP. So just because a problem is in, or a language is in NP, that does not necessarily mean that it can't be computed in polynomial time. So, and another thing that I see people do a lot of the time is this particular language or problem has a 2 to the n time algorithm, and then therefore is NP complete or is not in P or whatever. So I want to convince you that that's not a good argument. What about sorting? We know algorithms like merge sort, quick sort, whatever, n log n, n squared, whatever. Consider this sorting algorithm. On the input, the list of integers, look at every single permutation of the integers, of those n integers that are given to you. One of them is sorted, at least. Then when you find it, output it. How long does that algorithm take? Well, how many permutations of n numbers are there? N factorial. That's way beyond any exponential time algorithm. So just because there is some algorithm that takes an enormous amount of time does not necessarily imply that it can't be solved very quickly, like merge sort, for example. But what we're going to try to see is, are there problems that seem to be hard no matter how you approach it? There seems to be no polynomial time algorithm for them. And if we can show that, then, which we won't be able to do formally, but if we could show that, then we can show that P is not equal to NP. Okay? Any questions about that? Okay, well, think of P, for instance. It's the set of problems that you can actually compute the answer in polynomial time deterministically. Well, suppose that you had a really nice friend, right, for this supposedly really hard problem. And what he gives you is, okay, I solved your really hard problem for you, and I can do it really quickly. And then what should I say to my friend in order to make sure that he's correct? Yeah, show me a proof of some kind, right? Give me some kind of certificate or proof that you actually did solve the problem. So another analog of NP that we'll see right now is that we can talk about certificates that we can verify in a short amount of time. And by short amount of time, we mean polynomial amount of time. So what we're going to call a verifier for a language L is a deterministic, so not non-deterministic, algorithm or Turing machine or whatever you want to call it. Let's call it, what do I call it? I call it V for verifier, where L, that language, is the set of all strings for which there is some certificate that we can verify. So it's a set of all strings W such that there exists a string C for which V accepts the input W coupled with C. Okay, so this algorithm is, what it does is it accepts inputs of the form W and C, where C is what is called the certificate. So this is what is called the certificate. So it's an analogous type thing as an enumerator for a language, but here what we want is that it's going to verify whether a given string is in the language, coupled together with a supposed proof that that string is in the language. We'll see this many times with explicit examples. But the idea here is that my friend is telling me, yeah, this string W is in the language, and this C string is the certificate, the proof that it is in the language. So let's consider this. Let's define this problem. So a k-clique, or click, is a complete subgraph of a graph G with k vertices. So for example, if I have this complete subgraph right here, and then I may have some other vertices that may not have anything to do with that clique. Yeah.
Can you remind me what a complete subgraph is?
Yeah, so a complete subgraph, let's say among these four vertices, is that every single edge is present among those four vertices. So if I highlight in red these four vertices in the middle, then among those four vertices, every single edge is present. All four choose two vertices, edges are present. Yeah. Mm-hmm. There are many other k-cliques in here. For example, every single edge is a 2-clique because every single edge among those two vertices is there. There are several 3-cliques. Let's just do them in blue, let's say. So these three vertices form a triangle, what is called a triangle, which is 3-clique. So among those three vertices, every single edge is present. Okay? So we'll show that this problem is NP complete. But suppose that your friend says, I can tell whether or not an arbitrary graph given to you has a given k-clique in it very efficiently. What would be a proof that he's correct? Or that he actually did find a k-clique? Well, what would he have to tell me in order for me to verify that there is a k-clique in the original graph? How about the k vertices? How about a list of k vertices given to me? If he tells me, let's say that my k happens to be 4 in this case. If he tells me these four vertices right here, what should I eventually say? Should I say yes, there is a 4-clique, or should I say no, there isn't one? Yeah, I should say yes, there is a 4-clique because I can verify among those 4 vertices that every single edge is present. But what about in general? What would he have to give me in order for me to verify that there is a k-clique? What he would give me is a list of k vertices. Then I would make sure, were those k vertices in the original graph in the first place? Because if he tells me other vertices, then that's complete bogus already. But then I would need to check, among all pairs of those k vertices, is there an edge there? And if there isn't one, then I say, no, the certificate you gave me is wrong. So like, for example, if he, instead of these 4, he gives me these outer 4, then I can quite easily see there are some edges that are not present among those 4 vertices. So therefore I say, no, your certificate is wrong. Okay? Can I check that, do that verification in polynomial time? Yeah. Well, how much work do I need to do? Well, among the k things, I just need to check k squared roughly, number of edges, or pairs at least. And so that's clearly polynomial. So I can check this efficiently. Okay? So here, instead of just an arbitrary verifier, we're going to say a polytime verifier. V is a so this seems kind of redundant, is a verifier that runs in polytime in that input WC. So a verifier for the clique problem above is this W is the original graph. And this C is the list of k vertices.
So certificate is, it can be of any form as long as
Yes.
it proves.
Yeah, if there's some algorithm that can take it and verify it correctly. Yes.
So you have to have an agreement on the algorithm.
Yeah, and there are many ways in general for a verifier to work and what the certificate can be. So if you just say the certificate is the k vertices, then that seems to be the natural type of thing to do here. Yeah. Does that make sense? So the verifier is just a deterministic algorithm that takes this supposedly magic verification, this certificate string, and says whether or not the original input W really had that list of k vertices as a k-clique, for example. Okay? Okay, so we will prove here that NP can also be defined in terms of polytime verifiers. So instead of just thinking of this as n time n to the k, where I just union over everything, I can think of it as a polynomial time verifier. So if I wanted to solve some maybe NP complete problem or some really hard problem in NP, if I have a polynomial time verifier for it, it's an NP. which is a lot easier to think about instead of thinking of this non-deterministic algorithm that runs in polynomial time. If I can deterministically verify some certificate, then we're good. Okay, and we'll see examples of this. So let's see. So the way we're going to prove this is in two directions. So I should put proof here. If L is a NP problem, then let's say that it has a polynomial time verifier. Then if I can make a non-deterministic Turing machine that runs in polynomial time, that'll show one direction. So we're going to build a non-deterministic Turing machine that does two things. So the fact that it's non-deterministic, we're going to exploit right here. What certificate should I feed to this verifier? Because I know it has one from assumption. Well, I don't know what certificate to feed it. Have this non-deterministic machine guess it. Because it's a non-deterministic device, can it just guess the certificate? Yeah, because it's non-deterministic. So non-deterministically, select a certificate C of polynomial length. We better not have the certificate be too long because we need to have it be a polynomial time non-deterministic machine. We don't want it to, if it's longer than polynomial, then it's already longer than polynomial time to even write the whole certificate down. So we need to have it be a polynomial length. Okay? And then 2, and then all we're going to do now is just deterministically simulate the verifier and output what it says. So here we were able to convert this deterministic verifier and form the non-deterministic machine for the same language. Okay, so now we showed one direction. Now we just need to show the other direction. How do we convert an arbitrary non-deterministic Turing machine into a verifier? Well, let's see. How did we verify with, say, LBAs before whether or not the Turing machine accepted the input W or not? Well, what we looked at is the accepting computation history of M on W. So what we're going to do here is we're going to look at that accepting computation history and letting that be the certificate. Because that is a proof that the machine accepted the input W. So if L is an NP and has a non-deterministic machine for it, then let the certificate be the accepting computation history of that machine on W, or whatever the input is. And that's it. It's actually a rather short proof, but it's quite a powerful result in saying that instead of thinking of these non-deterministic Turing machines, you can think of the certificates instead, which it seems to be a lot easier for showing that something is an NP. Any questions on that?
We don't need the polytime verifier when it's in P
Because we can just simulate the thing anyway. Yeah. The simulation in that case would be the certificate because it runs a polytime anyway. So, yeah. Certificate is just a string, and the verifier is just a machine that on input W and C will accept exactly when the original string W was in the language. So it's kind of like a proof that W is in the language. No, it's just a string, but the algorithm takes that particular string and does something with it. Like in the case of K-clique, it was the K vertices, and the verifier would be among those K vertices, does all K2 edges exist or not? Yeah, it's just a proof of whether W is an L or not. Yeah, it's the same thing, certificate and proof. We'll see many examples of this, don't worry. Okay, so let's take a look at what the world would look like according to most theoretical computer scientists. This is not a proven world, unfortunately, but it's what most people think. So we're going to assume, unless I tell you otherwise, that P is not equal to NP. Most people believe it is, including myself, and you should too, at least until after the final. But we're going to assume P is not equal to NP unless I tell you otherwise. Well, we're going to think of P as being efficient algorithms. So if you have an n to the 100 algorithm for some problem, we're going to think of that as efficient. Now, all sane people wouldn't think an n to the 100 algorithm is efficient in the practical sense. But in the theoretical sense, we're going to think of P as being efficient algorithms. And anything that's more than polynomial time to be a not efficient algorithm. So what if I can show you a problem that we at least believe is in NP, but is not in P? That would be actually good to know whether a problem that I'm working on or you guys are trying to solve in your day-to-day job is actually in NP, but not in P. Or we can actually prove that maybe that is the case, that there is a separation between NP and P. Well, if we can find such a problem out here, that would be really nice. But how would I prove what type of problem that would look like? Well, it seems to be a really quote-unquote hard problem, right? Well, what does hard mean in this case? Well, one way we can look at it is if we can solve that particular problem very quickly in polynomial time, then every problem in NP can be solved in polynomial time. So if I can solve this supposedly hardest problem in NP really quickly, then all the problems in NP can be solved quickly as well.
Yeah, difficulty is what then obviously needs to be defined.
Yeah, we'll define that, yeah. But that's an intuitive idea. If I can find some hardest problem out in NP, supposedly not in P, then that would be really helpful. Okay? So this is where all the fun starts. So we're going to use the idea of reductions like we did to show things that were undecidable before. But in the case of here, we're going to have reductions between NP problems. So I'm going to reduce a known NP problem to a problem I'm trying to solve. And if I can solve this particular problem really efficiently, then I can solve the original one efficiently as well. So, but what I said, if we want this problem to be the hardest one in NP, then every problem in NP better be not nearly as hard as that one. So if I can solve that one efficiently, then every other one can be solved efficiently. Okay? So a polynomial time reduction from A to B, and we're going to assume A and B are both NP problems, is a function f from A to B, so that f of, no, not that way, that if we had a string that was originally in the NP problem A, if we apply the function f to that particular input, then I get something in B, because the function's from A to B. But what we want here is not only for this function to not take too long to run in polynomial time, but we want the answer to be the same. So if W really was an A, f of W really better be in B. And if W was not an A before, f of W better not be in B either. So what is called answer preserving. The answer is the same on both sides. So the reductions that we're going to see are just Turing machines that take inputs, exactly the same as before. Okay, and we write this as A less than or equal to, with a subscript P, B. And so here we call this A polynomial time reduces to B. Okay? So, does that make sense? No, time reduces to B. So, we kind of saw this kind of reduction before when we showed that things were undecidable, but we let those reductions take an arbitrary amount of time. We didn't restrict any amount of time unless, as long as it was a finite amount of time. Here we have to restrict it to be polynomial time, because if I allow you, say, exponential time to convert from this NP problem to this other NP problem, then I might as well just solve the problem in that process anyway. I better not let the process from problem A to problem B take longer than it would have originally took to solve the original problems anyway. So we have to restrict to polynomial time here. Okay? Any questions so far? Okay. So here's another term that's not quite as misused as P and NP, but it's very close to taking the top prize for that. So let's see. We say that L is NP hard if for every other problem B in NP, B polynomially time reduces to L. Yeah.
So how do you define difficulty in terms of?
Yeah, I'll go over that in 1 second. So I say that it's NP hard if every single problem in NP polynomially reduces to that one problem, or language, if you want to think of it that way. Why does this get what we want? Well, if L was in P, or is polynomial time solvable, well, let's see. Take your favorite NP problem, do the polynomial time reduction to L, and then solve it with the polynomial time algorithm. So polynomial times polynomial, I think is still polynomial. So this actually tells us something important. If L is in P, then P equals NP.
It's because the one-to-one correspondence between the function mapping, right?
The function mapping doesn't have to be one-to-one.
Oh, okay.
The answer has to be the same.
The answer has
Yeah, but the function doesn't have to be one-to-one onto anything. Yeah, there are actually, no, that's not quite right. There are some problems that like take an infinite size domain of A and map it to 2 elements.
Okay,
Yeah, it has to be 2, but it can't be 1 actually, but you can actually map it down to 2. So it doesn't have to be one-to-one or onto or anything. Okay, so this really does capture what we want. If we can solve L really efficiently, then we can solve everything in NP efficiently. But we're not quite done. We say that L is NP complete if L is NP hard and L is also an NP. So this notion of complete means that you're a really tough problem for that particular class of languages, in this case NP, and you're also belonging to that class. Well, why do I make this distinction between NP hard and NP complete? Take the language ATM, which is undecidable. It's also NP hard. Okay? So just because it's NP hard doesn't not tell you anything about how fast you can solve it or how slowly you have to solve it, necessarily. NP complete says you must be an NP and be an NP hard. Okay? Any questions on those definitions? So we don't have an NP complete problem yet to work with. So we need to think of what would be the first NP complete problem. So what we're going to do here is we're going to prove the first NP complete problem that was ever proved. So that problem is called CNF Satisfiability. And this was proved to be NP complete in the early 1970s, and I'll give you the authors in a bit. So what is this problem? So the input is of the form Boolean, should learn how to spell Boolean, Boolean variables. Let's call them x1 through xn. Boolean operations. And the ones that we know quite well are and or not. So variables can appear in what is called positive form, which is xi just by itself, or negative form, which is xi bar, or that's how it's written. So for example, if I set xi to be true, then the positive form instance of that variable would be true, and the negated form would be false. Okay? Let's see. What we're going to define now is a clause. So what this is an or what is called a disjunction of what are called literals. And these individual, either positive or negative form, those are literals. So for example, I could have a clause that looks like x1, so this v right here, that means or. x1 or x2 bar or x3 bar or x4, let's say. Maybe I can have a repeat of the unnegated form of x2 if I wanted to. Okay? So this reads x1, the variable x1, or not x2, or not x3, or positive x4, or positive x2. So if I happen to set x1 to be true, x2 to be false, so x2 bar would be true. Let's say x3 is true, so x3 bar is false, good. And then x4, let's call it false. And then before we said x2 to be false, I think. Yeah, so then therefore this last occurrence would also be false. So true or false or false or false evaluates to true. So that particular assignment of variables with values is true. Okay? And last one, I think. Formula is a and or what is called conjunction of clauses. And I don't restrict how short or long each individual clause is, and I don't restrict how many ands of clauses I'm going to do. So let's look at an example. So if I have x or y or not z, and, so this wedge right here is and. Let's say x bar or y, and think of a good example. Y or z or z bar. And so here are three clauses, each of which has either 2 or 3 literals. It doesn't matter how many. And they're conjuncted together. So the truth value of whatever the 3 clauses are is anded together. Okay? And we say a formula is satisfiable if there exists an assignment to the variables to make the formula evaluate true. So like the formula above that only had 1 clause, that is satisfiable because we gave an assignment to the variables to make the formula true. There may be other assignments to make the formula true, but as long as there's at least 1, I say the formula is satisfiable. So let's see. I actually don't know, but because I made it up on the spot, but is the second formula satisfiable? Well, let's see. In this clause right here, I can pick z to be whatever. So and actually, do I need to look at y in that clause? No. So as long as so whatever value of z I pick, that clause is true. So let's not even look at that clause.
Since you have an x and an x not, this first clause, x.
Well, let's make it a little easier on ourselves.
Depending on what y is, it's either true or false right away.
Yeah. So let's see. What if I pick z to be false? Then this clause is true because it's always true, depending on whatever value of z I pick. What about this clause?
That's true.
That's true because z bar is true. So that's satisfied. Is this one satisfied yet?
No.
No. So how could I satisfy it?
A true y or a
Yeah.
false x.
Yeah, either one. So one assignment is x can be either true, let's make it true, it doesn't matter actually. Y to be true and z to be false. And so now since we found an assignment to make the formula true, we say the formula is satisfiable. And so you may be wondering, what in the world? Do people really study this problem? It turns out, yeah, there's some people who do, but the reason we study this problem is that it has such nice structure to prove other problems to be NP-complete. If we can show that this problem is NP-complete, then we can do a whole bunch of nice reductions that are really easy to show that they're also NP-complete.
This is basically a net list too.
What's that?
This is basically a net list too. Don't worry about it.
It's an ATM for undecidable problems. How about that? Yeah. So any questions about the definition of what satisfiable means? And actually one more definition. Just the definition of the language. So we define CNF Sat to be all of the formulas. So we're going to call it phi here, such that phi is a Boolean CNF formula. Yeah, that is satisfiable. So this is the problem, the decision problem that we're worried about. We have to answer except if the formula given to us is satisfiable, and reject if it's not satisfiable at all. Well, I don't know whether this is in P or NP yet, but what is an upper bound on how long this takes? Well, how many possible assignments are there? Well, 2 for the first variable, 2 for the second variable, 2 for the third variable. If I have n variables, how many assignments do I have? 2 to the n. So, and for each one, I just check whether the formula is true. So, we can actually easily see that CNF Sat belongs to time of 2 to the n. Now, from that, don't say, therefore it's not in P. Just like the sorting example, just because we have an algorithm that takes a long time doesn't mean one doesn't exist that runs faster. Okay? Cool. But we believe that it must take at least polynomial time to solve this problem. And we're going to prove that by showing that CNF Sat is NP-complete. And the 2 authors who independently showed this were Cook and Levin in 1971 and Levin in 72. I think maybe 73. What's that? Yeah. But it really was completely independent at the time. So it's now called the Cook-Levin theorem. So let's see. If I want to show that CNF Sat is NP-complete, what things must I show? Show it's an NP. Let's do that one first, because that's far easier. So CNF Sat is in NP. Well, we could think of this in 2 ways. We can think of it in terms of making a polynomial time non-deterministic Turing machine for this problem, or what else could I do? We can make a deterministic verifier for this problem. What would be a certificate for this problem to figure out whether the formula is satisfiable or not? Well, one such way is a satisfying assignment. So if I am told, set the first variable to be true, set the second one to be false, third one to be true, then how do I verify whether that assignment is correct or it makes the formula true? Why don't I just evaluate the formula, right? If any clause is false, then the whole formula is false. So the certificate is the assignment to the variables. then verify if the formula is satisfied by this assignment. Okay. So it's the assignment is the proof, right? If the assignment that's given to me is false, it makes the formula false, then I just say, no, that certificate is wrong. I'm proving that the certificate given to me, and in this case is the assignment to the variables, actually does make the formula true. Okay? So we now know it's an NP. But what else do I need to show? Is NP hard. So this will take probably 40, 50 minutes to do. But we'll see. Well, this is what makes the first proof so hard. Do I have an NP complete problem to work with yet? No, I don't have one. And it says that in order to show that a problem is NP hard, I need to show that every problem in NP polynomial time reduces to this problem, CNF Sat. How many problems are in NP? Yeah, it actually is uncountably infinite. Well, I mean, we do have 4 lectures, right? we can make some good progress, but I don't think I can claim that as NP hard then, if I just start enumerating examples and show a reduction. So maybe that there is something in common between all NP problems. What does it mean for a problem to be an NP? Well, we had those 2 definitions. Either it has a certificate that runs determined with a verifier and everything, or what's the other one? It has a polynomial time non-deterministic Turing machine for it, right? That's what it means to be an NP. Oh, maybe we can look at the computation of the machine on that particular input and make a formula that's true if and only if the computation history is actually correct. So I'll say it again. We want to show that for every problem in NP, it reduces to CNF Sat. So how do we do that? What do have all NP problems have in common? They have this polynomial time non-deterministic machine. That's what it means to be an NP. Well, what we could do is, since they run in polynomial time, we can look at the computation of the machine on whatever input. Yeah.
Does that mean they all run on the same theoretical machine?
No. But whatever fixed language I'm looking at, say B in this case, then I know there's some machine for it. I don't have to think about anything about that machine. I just know that it exists. So let me recap. They have an accepting computation or a computation of polynomial length on whatever input that they're given. Let's make a formula that's true if and only if that computation is accepting. Okay? So that's what we're going to do after the break. So let's take a break for 5 minutes then.